On October 8th this year, the Nobel Prize Committee announced this year's Nobel Prize in Chemistry to three researchers working on the development of metal organic frameworks. The prize was awarded to Susumu Kitagawa, Richard Robson, and Omar Yaghi for the development of molecular framework materials, which have sparked a huge field in material science and chemistry in general. What are the details of this prize now? And what is its importance also towards the field of material science and petri science in particular? Richard Robson, in the late 20th century, discovered that when playing with structural models such as diamond, which is depicted here as a classical diamondoid net, substitution of individual carbon atoms in that diamond lattice by tetrahedral molecules, such as these ligands depicted on the top right, could result in the formation of isostructural framework materials that bear the same sort of structural topology as the diamond net, but due to the larger size of the molecular building blocks, results in a vast expansion of this isoreticular net under the production of cavities inside this framework. And so he really laid out the blueprint for the establishment of molecular framework materials that are based on coordination chemistry consisting of organic building blocks, organic ligands, with combinations of metal ions. Later on, Susumu Kitagawa discovered that these voids, which were originally after the synthesis filled with solvent, can be emptied out and refilled with gas molecules. And he really drove forward the field of gas adsorption in these materials. But in addition to this, already in 1998, he discovered and proposed that there are different generations of framework materials, some of which are able to change their structure upon uptake and release of certain gas molecules, a field that is nowadays referred to as soft porous crystals or flexible metal organic frameworks. Metal organic frameworks really reached the public domain with the early discoveries of Omar Yaghi, who overcome initial limitations in the stability of framework materials constructed by Kitagawa and Robson by incorporating carboxylase-based organic ligands, which were then coordinated to multivalent transition metal ions, or in the case of MOF5, metal oxo clusters. And it was really the demonstration of this MOF-type framework in this paper from 1999, where Omar Yaghi and co-workers were able to demonstrate that these frameworks are able to withstand solvent removal, and in addition to that, featured extremely high surface areas, almost an order of magnitude higher than comparable zeolite materials, which were sort of the benchmark for microporous materials at the time. And it was Michael O'Keefe, who was one of the authors of that initial paper, who came up with the idea of demonstrating the void and cavities in these materials with the yellow sphere. And to date, he claims that his biggest contribution to the field of metal organic frameworks were actually the yellow ball inside the pore. So if you ever come across MOF illustrations and you see these spherical balls in the center of the pores, this is the illustration of the pore void that make up a large part of the framework materials. It was Yaghi in the early 2000s who further developed this concept of what he referred to as reticular chemistry, so a chemistry based on the underlying net of these framework materials. And he was able to demonstrate that you can change and functionalize the organic linkers with different functional groups while maintaining the same kind of chemical connection bonds, in this case carboxylates, and introducing additional chemical functions on the side group. He also demonstrated that it's possible to extend the length of the organic linkers in a series of so-called isoreticular frameworks, which allows to drastically expand the pore size of these materials, as illustrated here by the growing size of the yellow void inside the framework. And already at this time, researchers were strongly able and focusing on utilizing this large pore space for the uptake of gas molecules, in particular methane, hydrogen, but also greenhouse gases such as carbon dioxide. Over the past sort of 20, 25 years, the field of metal organic framework research has really kicked off. And there are literally hundreds of thousands of MOF structures reported each year, with a total number of MOFs reported to date in the 100,000s. We can see here several early and important examples in the field of MOFs, for example, MOF 303, which is heavily used for water adsorption at dry desert air, MIL 101, a very large mesoporous framework material utilized for catalysis, for example, UIO 67, a material based on zirconium, which was one of the early examples to be able to withstand harsh acidic conditions without decomposition. Civ8, a very hydrophobic material that can be easily synthesized by the utilization of imidazoles with divalent tetrahedrally coordinated transition metals, which reassemble structure types known from zeolites, but with an expanded pore structure. Or CALF20, a very recently discovered material which has a very high affinity to carbon dioxide, which is currently used for carbon dioxide capture from flue gas of concrete factories. Or this very large porous NU 1501 material, which is able to utilize different geometries of ligands in a very channel type pore structure. But beyond the large variety of different structure modes that MOFs can take up, there's another aspect that allows us to enhance the structural functionality in these frameworks. Now, Yaghi was able to demonstrate that we can generate so-called isoreticular frameworks by adding ligand systems with the same structural topology and coordination motive, but additional functional groups. And here you can see a series of terephthalate-based organic ligands, which can all be incorporated in the same type of MOF5 framework. And we can also mix these different linkers in different ratios in the construction of metal organic frameworks, generating materials which now have small nanoscopic clusters of certain chemical function, or an alternating distribution of these different ligands, random distributions, or even raising the complexity level to mixing up to 8, 10 different organic ligands in a single crystalline material. Now, early on in the field of metal organic frameworks, their utilization in industrial application was hampered by the aspect of stability. In fact, MOF5, based on the zinc oxide clusters, is relatively hydrolytically unstable. So when it is exposed to especially vapor water, it will decompose into more stable zinc oxide. Now, of course, for certain applications such as gas capture, an enhanced stability is a critical aspect. And over the years, the incorporation of high valent cations such as zirconium 4+ or iron 3+, or chromium 3+, research that was primarily done by Gerard Ferret, also one of the big founding fathers of the field of metal organic frameworks, were utilized to generate more stable and reliable framework materials by also utilizing strengthening coordination bonds or protection of coordination bonds, for example, by hydrophobic groups surrounding the metal nodes. Also enhancing the density, moving away from very highly porous framework materials down to microporous materials, drastically enhance their mechanical and temperature stability, including mesoscopic structuring and coating of these materials. Now, if we consider metal organic frameworks from the perspective of a material scientist, we can now really think about the classical approaches towards making new materials. And in general, people would approach this by first selecting the composition, and on classical solid-state materials, selecting elements from the periodic table. Secondly, the structure of these different elements and how they are connected is what provides materials with their critical functionality and aspects. Now, in MOF chemistry, we can drastically enhance the classical space of traditional solid-state materials by utilizing a hybrid composition that involves now the combination of a large space of transition and main group metal ions with organic ligand molecules, and the ability to generate structures of frameworks which are not achievable with classical solid-state materials. In the essence, metal organic frameworks allow a chemist or a material scientist an unlimited playground of molecular Lego by which we can tailor and design our framework materials with various different aspects utilizing a large structural and compositional space. This large compositional and structural space can be extended by multivariate systems, such as, for example, the combination of ligands of same structure but different functionality. But also recent research towards aperiodic structures, which now starting to enter fields of quasicrystals, which were also already awarded the Nobel Prize. So we can generate aperiodicity and structural features unattained in classical solid-state materials. In addition, we can combine aspects of classical solid-state materials, such as a tunable band structure, with the accessible interior of these structures via the large pore space that is usually part of metal organic frameworks. This allows us an unthinkable platform to incorporate molecular function in the solid state and making those molecular functionalities accessible for guest species. In addition to this, we can also utilize these materials for uncommon physical properties, such as electrical or thermal conductivity, but in addition to that, also features such as negative gas absorption or negative thermal expansion. And of course, these hybrid systems now for the first time allow us to really combine the large structural and functional space of organic materials with inorganic function well known from classical solid-state materials towards hybrid systems. Now, over the years, metal organic frameworks were heavily focused with areas of application in the field of gas storage, gas separation, simply because porous materials are able to capture and take up and maintain gas molecules inside their pore interior. But the features of metal organic frameworks, such as long-range order, such as crystallinity, porosity, or the modularity of being able to exchange building blocks, and the abundance of certain active sizes also motivated researchers to consider MOFs as materials in battery science technologies. And around 2010 towards 2015, the first examples of utilizing metal organic frameworks as components in battery applications such as cathode materials or in the electrolyte systems have been proposed. And to date, there's really a growing space of metal organic frameworks being researched in the context of battery science. This involves, of course, MOFs and MOF composites as the active materials because they feature a large ability to tune the pore structure, which is important for the transport of ions, for example, but we can also tailor the morphology important for the functionalization of electrodes or electrolyte systems. In addition to that, a large growing field of research also is considering MOF-derived materials. Now, I'm sure the Nobel laureates that are being awarded the prize during this Nobel Week are maybe not so happy about people pyrolyzing or burning their tailor-made materials into composite materials. However, a very good dispersion of metal ions in an organic matrix really allows you to tailor composite materials with structural features unattained by any other synthetic method in material science. Now, metal organic framework materials have also entered the post-lithium storage cluster of excellence, POLiS, which Ulm University and KIT are part of, and now in our new funding period, which will start in January next year, joined by our partner in Gießen. And POLiS has already started to incorporate the science and chemistry of metal organic frameworks in formulating active components of battery materials. In 2022, Jürgen Janek and co-workers have started to incorporate the concept of a quasi-solid state electrolyte system based on a zirconium MOF UiO66, intrinsically functionalized with an ionic liquid in its pore interior. And they have utilized the semi-solid electrolyte system for a very challenging kind of battery system that is being researched in our post-lithium storage excellence cluster based on magnesium. Now, magnesium batteries are promising battery technologies due to the potential high theoretical charge density, but magnesium as a divalent small cation is very difficult to transport in classical solid-state materials, which usually feature relatively low ionic transport properties. So this approach was further developed by other research groups at Ulm University from Timo Jakob and co-workers, utilizing now mixed metal organic frameworks as an efficient solid-state electrolyte for magnesium-ion batteries. Now, utilizing metal organic frameworks, which have been known for years, even before the term has coined, based on very simplistic four-main system. They feature very small ligand systems and now allow, in the combination of mixing different MOF components, to establish electrolyte system with extremely high ionic mobilities. This research was extended by further tuning the MOF structure and its incorporation of including different guest species and magnesium ion composites to further tune the properties of these electrolyte systems. Yannick and co-workers here in collaboration with Klaus Müller-Buschbaum were able to use a one-dimensional port channel system, magnesium MOF 74, to also enhance the activation, or to reduce the activation barrier and enhance the ionic conductivity over a wide temperature range, and further pushing this field of semi-solid electrolyte system based on MOF material. And finally, very recent work now illustrates that we can further tune the MOF chemistry by incorporating heterovalent ligand systems, which also feature additional donor groups, towards further enhanced semi-solid electrolyte systems in magnesium batteries. So what POLiS 1 has started in their funding period on utilizing MOF materials in the electrolyte system, the newly starting POLiS 2 cluster will continue on this, further extending on combining the knowledge from organic and inorganic cathode materials, further moving towards these hybrid MOF-based electrolyte and cathode systems towards post-lithium energy materials. I'm sure that when the laureates for the Nobel Prize first invented these materials, they didn't really know how large the field of metal organic framework science would grow over the years. But it's safe to say that their underlying chemistry and the concepts that they have established over 30 and 40 years ago has now sparked a huge field of research that is branching into different kinds of applications, including battery science that is researched here at POLiS Cluster of Excellence. So it's my heartfelt congratulations to the laureates, which will receive their medals during Nobel Week this week. And we are very much looking forward to continue in their spirit of bringing molecular function into the solid state and playing and designing Lego on the molecular level. Thank you very much.